All right, so number 2, right, on the homework?
Yes.
So number 2 on Pearson, number 16 in the book, page 740. And the function is, in the book, I'll work this one, Thomas, and you can make adjustments, 1 plus 4x.
Okay.
And we want to center it at 0. So we're talking about the Maclaurin series. The Maclaurin series is a Taylor series where the center is 0. So what we have to do is figure out the coefficients. And the coefficients, a sub k, turn out to be, we derive this, we don't, and so we're remembering it, we don't derive it every time, we have a formula. And it turns out that it's the kth derivative evaluated at the center, in this case 0, divided by k factorial. So for every k, 0 to infinity, if we pick those coefficients, we get a power series that converges to our function. And so the k factorial, that's fixed. What we have to do on any given problem is, find a pattern for these kth derivatives. So, let's make a chart here. Let's see, here is the value of k, just the way we want to do it. And here is f k of x, and then we'll evaluate it at 0. So when k equals 0, we're just talking about the functional value. If you plug in 0, you get the log of 1 plus 0, that's just 0. So not a very interesting first thing, but we haven't even taken a derivative yet. The next thing to do is we take the derivative. And because of the log, we're going to put 1 plus 4x in the denominator, and then the chain rule says multiply by the derivative of the inside. Oops, wrong column. First derivative, and we get 4 over 1 plus 4x. Okay?
Can you tilt your camera up a little bit?
Oh, absolutely.
Thank you.
Thank you for reminding me. Is that good there?
Yes.
All right. So I'll give you a second to look at that.
Okay. Okay.
Okay. And to set us up for the next derivative, let's write this in a nice form. So the next derivative is nice and easy. We could use the quotient rule, but we don't have to. So I'm just going to lift that 1 plus 4x up and write it to the minus 1 power. And what goes at the end of this second row?
The end of the second row, that would be 4x.
Nope, we're plugging in
0.
4.
Just 4. Okay.
There's no x in the last column. It's a number.
Okay.
Okay?
Yes. Sorry. I'm getting a call from my grandpa.
Take it.
Someone else will be able to take it. Good. Thank
So
you.
take the derivative, pull the power down. And then we get 1 plus 4x to the negative 2. Then in this column times the derivative of the inside. Let me just, every time we take a derivative, we kick a 4 out.
Okay.
Select those in front.
Okay. So you squared the -4?
Yes.
Excellent.
You see, every time we take a derivative, the chain rule is going to kick a 4 out.
Okay.
Now, so 1 4 here, 2 4s there, 3 on the next row.
Okay.
And when you plug in 0, what do you get?
You get -16.
Yeah, but we're looking for a pattern. So let's write it as 4 squared.
Okay.
We're looking for a pattern. And we figured out a good chunk of it, but there's one piece left. So let's take another derivative. So we have this -4 squared out in front. And then we're going to pull the power down. Well, that minus is going to flip this, right?
Mm-hmm.
And the 2 survives. And then we get 1 plus 4x to the -3. And then we kick another 4 out. So we've kicked a total of 3 4s out for the third derivative.
Okay.
And plug in 0, what do you get?
2 times 4 cubed.
2 times 4 cubed, perfect. Now, we almost have it. I think if we do one more, we'll see the pattern. The fourth derivative. So notice that this minus sign is going to kick it back negative. We get that. And then I'm going to pull the 3 down. I have a 3. This 2 is still lurking there. And remember, we're going to kick a 4 out. So when we get done, we're going to have 4 powers of 4, right? And then we have 1 plus 4x to the -4th power. Should have made my second column a little bit wider. Okay, well, not William, Thomas?
Yes.
What do you get?
You get -3 factorial times 4 to the 4th.
Beautiful. Yeah, you see, we're building up a factorial. You could have said -6, and you would have been right. But we're trying to find a pattern, and you can see, because we're decreasing these powers as we go, that as we take derivatives, we're building up a factorial. So I think we can make a conjecture. When we're down to the kth derivative, when we get -1 to some power, we'll worry about that in a minute. Let's just write it to the kth power. Actually, when k is odd, the power is even. So how about +1 or -1? It doesn't matter. And then we have, so what factorial showed up here? 3, and which derivative was it?
The 4th.
4th. Now, in retrospect, we can say, well, look, 2, maybe that was really 2 factorial, and it showed up on the 3rd, and we could say, well, there's also a 1 factorial here. So what we think is that we have k minus 1 factorial. Is that right?
Yes.
Yeah. And that's it. We're plugging in 0. I mean, that's not it for the second column because it represents the function, but we're basically done with it. So we get -1 to the k plus 1 times k minus 1 factorial. So we do the work over there, and now we can write a formula for it. We figured this thing out. -1 to the k plus 1 times k minus 1 factorial. And then the formula says always you have to divide by k factorial.
Okay.
Following there?
Yes, but except for one thing. What happened to the powers of 4?
Oh, that was a super good question. Yeah, I left them off here. How many will there be here? 4. So the power ended up being exactly the same as the derivative. So 4 to the k. Excellent observation. Let's say I did it on purpose. You nailed it. Oh, I circled in red. I didn't quite capture it all. Here's the formula, and it just goes and gets plugged in right there in the numerator.
Okay.
We're done with all of this stuff. And we know the coefficients now. We could write out the Maclaurin series, but let's do one thing first. And you should always be on the watch. Notice that with this factorial here and that one there, almost everything cancels there. So we end up with a sub k equals, it alternates. We jog it by 1. And then all of these cancel all of those except the very last one, k, survives here. So we have 4 to the k divided by k.
Okay.
And I just remind us that when we evaluated the function at 0, we got 0. That was on that chart I erased. And so here is our Maclaurin series. Because a sub 0 is 0, let's start at 1. Minus 1 to the k plus 1 times 4 to the k over k times x to the k. Okay?
Mm-hmm.
I should think of another way to say that besides okay. We have enough k's as it is. So that is a power series. I mean, it happens to come from this, but it's a power series. And so what we learned about power series in section 2, we apply it. And we're looking for the radius. So we're going to take the ratio test. In section 2, we would call it for absolute convergence. When we learned that in chapter 10, we didn't really use alternating series, but in section 2, we learned how to modify it. So we're going to calculate the limit as k goes to infinity. We take the absolute value of this thing. Well, that's going to wipe out the minus 1 to the k plus 1. And I end up with 4 to the k plus 1 times the absolute value of x to the k plus 1 divided by k plus 1 factorial. Okay, so to apply the ratio test, it only works on series of positive terms, so we take the absolute value. We also learned in section 2, actually, this would have been in chapter 10 in the section on alternating series, that if a series converges absolutely, that is ignoring all the minus signs, then the series with all the minus signs included, it converges. So here we have, like is common, our formula is a fraction, and I've encouraged you to like skip the first step and we'll just invert the fraction we're dividing by. So I get this k goes on in the numerator, and then down below I get 4 to the k, and I get the absolute value of x to the k. So we're actually dividing the k plus first term by the kth term, but we're not writing that first step out. We're doing the division, invert and multiply. And then some wonderful things happen. So I have k plus 1 powers of 4 in the numerator, k powers in the denominator. What happens?
It's just 1 power of 4
Yeah,
in the
so
numerator.
the k plus, and we'll get rid of the 4 to the k. Similarly, on my x's, exactly the same thing happens. K plus 1 on top, k on the bottom. These guys go away. One of them survives. I left a factorial. Oh no, there should not be a factorial. K plus 1. Sorry, but did you see that?
Mhm.
I had an errant exclamation point right there. Well, then I get 4x, absolute value of x. And then let's pull out all the k's over here. I get that limit. And what is that limit, Thomas?
Times k over k plus 1. That would be um, -4 and 4.
Okay, so the limit is 4 absolute value of x.
Oh, okay. So -1/4 and 1/4.
Yes. Yeah, we need that to be less than 1, and therefore you saw it. And so r is 1/4, the radius of convergence.
Okay. Excellent.
Does it ask for the, well, I got the instructions right here. Yes, it does ask for the interval of convergence. So notice when I plug in plus 1/4, that 1/4 is going to cancel out. 1/4 to the k. It's going to cancel out 4 to the k. Can you see this okay?
Yes.
Those are going to cancel out. 4 times 1/4 is 1 to the k. And then we get alternating harmonic. Right? Just this k survives. It's alternating. And we know the alternating harmonic series converges. So
Okay.
at the upper endpoint, we get convergence. So we'll square that bracket off. At the lower endpoint, now the minus comes in. And so 4 times -1/4 to the k is -1 to the k. Which is the -1s then will cancel out, and we get the ordinary harmonic very close to it, and so it's going to diverge. And there's our interval.
Okay. Wow. Thank you.
You bet. There's a lot to do on that problem.
Yeah.
Maybe we got it all figured out. And it was a team effort. You caught my mistakes.
Thank you.
I led us forward.
Excellent.
So it kind of all comes down to how hard it is to find that pattern. This guy right there. Because we got to find it. And I tried to assign problems where the pattern showed up fairly quickly. And some of them, the derivatives get pretty gnarly, and I just tried to avoid those.
Okay.
Now, like number 15 in the book, it has an x squared in the parentheses. So when you differentiate, you kick out a 2x, and now you have to do the quotient rule every single time.
Ooh.
And yeah, we can do it. We absolutely can do it, but maybe it's not a good problem to learn.
Yeah.
Save it for some day down the road.
Okay.
All right. Do you have any other questions?
Um, check. Hmm.